Perhaps in the interest of time, we can go ahead and get started. Welcome everyone to this journal club sponsored by Physical Review Fluids. Today, we're going to be hearing a presentation and talking about a recent paper in the journal, Numerical Investigation on the Heat Transfer in Wind Turbulence over Breaking Waves by Minlu, Zixuan Yang, Guowei He, and Lin Shen. And Zixuan will be giving the presentation. The plan here is to have about a 15-minute presentation and then 15 minutes of Q&A afterwards. Feel free to type questions into the chat or afterwards use the raise hand feature in Zoom and we can ask your questions verbally. And before that time, please mute your microphones so we don't have any distractions. So Zixuan, why don't you take it away?
All right, thanks, Professor Olit. So thanks for being here. So I'm going to talk about our recent work on the numerical study of heat transfer over breaking waves. So sorry. All right. So this is the flow I'm going to talk about today. You can see wave breaking, and what we focus on is the heat transfer. So background shows the temperature field. Now, first, let me say something about the background. Basically, the weather forecast of a strong tropical cyclone nowadays, the climate models, they can make a nice prediction of the trajectory because the trajectory is mainly determined by this kind of large-scale motions. But for the intensity, the prediction is not quite satisfactory, because the intensity is influenced by many small-scale dynamics. So among which the wave breaking plays an important role. So that means the forecast of a cyclone, if we want to make a nice prediction of the intensity, it turns from a meteorology problem to a mechanics problem. So that's why we do this research. So speak of the numerical simulation, actually, there are different ways of studying the interaction between atmosphere and ocean. So like for this type of simulation, the wave is treated as a bottom boundary. Then for this way of simulation, we cannot simulate the breaking wave. And we can also simulate a breaking wave, but most previous studies does not consider the airflow. So what we do is to couple the wind and wave to solve the flow of wind and wave together. So this is the case setup. We consider different wave ages. So actually, in our paper, we mentioned 5 wave ages, but in my talk today, I'm going to focus on these 3, which represent young wave, intermediate wave, and old wave. And so this is the case setup. We have a wave at the bottom, and then we develop the wind, and here is the grid resolution. The temperature is treated as passive scalar because the wave breaking is its characteristic time is relatively small, so that we do not try to consider the buoyancy effect. So, and here is the numerical method. We solve the air and water on Eulerian grid with the interface captured using a couple level set and the VOF method. And we also have developed a temperature solver, basically to ensure the numerical stability for temperature. We need to evolve both the temperature equation and the convection equation of the volume heat capacity. And then we have this temperature solver. So now let me say something about results. So before I go to the temperature field, I need to say something about a previous paper of mine that is about the momentum transfer over breaking waves. So basically, this is the process when wave is turned over and start to plunging, right? And we can see that in front of the wave crest and over the wave crest, there is a high speed region. So that means the wave transfers momentum from water to the air phase. And we can also see the velocity profile here. And for different wave age cases, a small wave, a slow wave, or a fast wave, although the wind profile can have different pattern, especially for this fast wave, it has a reverse gradient because the wave is fast that drives the wind to move. So there's a reverse gradient. But if we look at the effect of wave breaking on the velocity, we find that actually after wave breaking, the velocity increases. That means the wave breaking transfers momentum from the water phase to the air phase. Now let's look at the temperature field. So this is the temperature for a slow wave. That we can see that actually after wave breaking, the temperature increases. So this is the profile before wave breaking, and this is after wave breaking. So there's one thing I need to say is that for the case setup, we have a lower temperature in water and higher temperature at bottom. So so if the opposite way, then we should change all the things to the opposite way. But now let's use this as an example. So that temperature increases for the slow wave case. But for the fast wave case, we can find that after a slight increase, eventually the temperature decreases. So we can have a guess what happens to the intermediate wave case. That temperature increase, temperature decrease, does that mean the temperature is close to a constant that remains almost unchanged for the intermediate wave case? But the answer is no. We can find that for the intermediate wave case, the temperature decreases. And the decrease, the degree of the decrease is even larger than that for the fast wave case. That means there is a non-monotonic effect of the wave breaking on the temperature, on the heat transfer. So usually this type of nonlinear, non-monotonic behavior is correlated with some nonlinear effect. So then, if we look at the contours, we focus on these two intermediate and old wave case, and we find that actually there is a low temperature region after wave breaking, right? The low temperature region occurs over the wave crest. Then let's take a look at the mechanism a little bit. So to investigate the mechanism, we can take a look at the temperature flux. So this page shows temperature flux for the slow wave. What we find is that actually after wave breaking, the temperature flux increases at a certain attitude that is away from the surface, and there forms a negative gradient here. So the temperature tends to be transferred from a high flux region to a low flux region. So that means the temperature transfers from the higher altitude to a lower altitude. So the temperature here is larger. Then when the temperature is transferred to the bottom, the temperature at the bottom increases. So this is the case for the slow wave. And what we find for the fast wave, as actually the temperature, the flux gradient is reversed. So that means the temperature transfers from the bottom to the top, so that from a low temperature region to a high temperature region. So that leads to the decrease of temperature. Then we can look at the intermediate wave case. Actually, we also see a negative gradient here, and what we find is that the decrease more. And if we compare these two cases, intermediate wave with the fast wave case, what we find is that actually the flux, they show almost, similar comparable magnitude. But we need to mind is that actually what matters is that if we derive the equation, we find that actually what matters is the flux non-dimensionalized using the wave phase speed. Here it's non-dimensionalized with wind speed. So if we do that, actually they show difference. And actually initially there is a balance condition that the flux is balanced with other fluxes. And so that means what really matters is the degree of the deviation of this flux from the balance status. So you can see that for the intermediate wave case, actually the the deviation is much more significant. So that's why the temperature decrease for the intermediate wave case is more significant than in the fast wave case. So to go deeper, we can take a look at the decomposition of the temperature flux. Actually, based on a phase average method, we can decompose the total flux into a wave-induced part and a turbulence part. So for the fast wave, for the slow wave case, actually what really what really determines the total flux is the turbulence-induced flux. So here, and the wave-induced flux is relatively small. It's not that important. So this is for slow wave case, because for this slow wave, the wave speed is much smaller than the wind speed. So the turbulence in the wind dominates. For this fast wave case, it's opposite way, and you can see that for the total flux, actually it's determined by the wave-induced part, and the turbulence-induced part is relatively small. And then if we look at the intermediate wave case, actually we can see that both wave-induced flux and the turbulence-induced flux, their magnitudes are comparable. So then we try to figure out what happens to the turbulence-induced part. There must be some interaction between these two parts to enhance the turbulence induced flux for this intermediate wave case. So we can look at the time history, and it shows the same thing, that for intermediate wave case, the turbulence flux actually it increases. So you can see that it increases significantly. But for the fast wave case, it also increases, but it's much more. I mean, the increase less than this intermediate wave case. Well, then let's go deeper to look at the mechanism. Then what we find is that actually the temperature flux, the turbulence flux, okay, it occurs over the wave crest. That's why we find that the low temperature also occurs over the wave crest. So this is for intermediate wave case. So we can see that the turbulence magnitude is much larger, the contour, right? So it's deeper color than in the fast wave case. And if we look at its transport equation, we can see that there is a production term that dominates the behavior of this vertical flux. And this production term is written as a streamwise flux multiplies the streamwise gradient of vertical velocity. And then we put these two quantities together, we find that actually the gradient of velocity overlaps with the positive streamwise flux for the intermediate wave case. But for fast wave case, there is no such overlapping. So that means that's why the production is larger in this intermediate wave case. Then we can further take a look at the streamwise flux. Actually, it's mainly produced by this term, which is the interaction between a streamwise velocity fluctuation and a streamwise temperature gradient. So then if we look at the whole process, actually what we find is that at the beginning, there is a vertical velocity that is generated by wave breaking. And then it brings the low temperature to a higher altitude to produce a temperature gradient. And for the slow wave case, actually the wave effect is so weak. So that means there is no such type of temperature gradient. We can see that the isoplane of the temperature is almost straight for this fast wave, slow wave case. So this process is absent for slow wave case. And after this, for the fast wave case, actually the streamwise flux interact with the velocity gradient. And as we said before that there is no overlapping of these two processes for the fast wave case. So this process is absent in the fast wave case, so that the turbulence flux is not that strong in the fast wave case than in the intermediate wave case. So eventually, together with the wave-induced flux, then we have the total flux, then it influences the mean temperature. So basically here comes to the conclusion. I think 15 minutes is okay. Yeah. Thanks. So finally, I would like to let me have 1 minute to thank my co-authors and also thank the program that support my research. And also I would like to acknowledge Professor Beverly McCann for handling the paper and also the anonymous reviewers for providing their very helpful comments. And also thank Professor Olitu for host this event, and also thanks Professor Loga for organizing the event before this. Yeah, thanks.
Fantastic. Thanks very much for that. So the floor is now open for questions. Feel free to type them into the chat or use the raise hand feature. That's probably the best way to moderate this. And then you can unmute and ask your question. Maybe I will try to get the ball rolling a little bit. So I'm not really in this field, so this isn't sort of my wheelhouse here, but you have an argument that part of why the intermediate case is the sort of the case where you see this optimal coupling. It comes down to sort of a simple argument that the oh, there's a comment in the chat to please put the conclusion slide back up.
So this way, yeah.
That's sort of this the wind speed and the wave speed are similar at that point, so you can things sort of match up there. But I was struck a little bit in this estimation of wave age, you're comparing the phase speed and the friction velocity, and all of them are well above 1. So that in fact, the intermediate case is something like 12. So about an order of magnitude bigger than where you might expect some sort of direct relationship.
Okay.
Does that imply that these are the wrong scales to use, or?
So basically, what we use is velocity for wind. We use friction velocity, right? So friction velocity is actually its value is relatively small. So if we look at the velocity, this is the velocity, right? So this is the velocity normalized using friction velocity. So we can see its value like something 12 or 15 here. So that means if we use the wind speed here, it's actually the same as the wave phase speed because the wave age is also 12, right? So C over U is, yeah. So they have the same magnitude. Yeah.
Great. Thank you. Ashwani, would you like to ask your question? Yeah. Great. Or I can ask it.
Okay.
Oh.
Yeah, I see this question about
the
numerical method, right?
Yeah. So the question, actually, I'll just read the question out, asking which method and tools that you used in the simulation. What were the methods for solving the problem?
Okay, so yeah, I didn't have time to go to details of our numerical method. We use a finite difference method, and the wind and the wave, the air and water phases are solved together on a Eulerian grid, and we use a coupled level set and the VOF method to capture the interface. So so for level set method, actually it can capture make a accurate prediction of the geometry, like curvature and normal direction of the interface, but it has some problem with mass conservation. And when it's coupled with the VOF method, the VOF can conserve the mass to a machine precision. So then we have both mass conservation and the accurate prediction of the wave geometry. So this method is especially important for those interface with large curvature or small interface structures. Yeah, so that's basically the numerical method.
Great. There's another question here from Yoshio Matsuki, asking if you have any chance in the future to carry out environmental monitoring to compare with the numerical simulation.
Yes, actually, this is actually very important thing that we should consider in the future. Actually, you can see that for in terms of the simulation, we have to set up the case with a very steep initial. Let me show you here. Yeah, how about this one? So if we look at the video here, we need to set up the simulation starting from a very steep wave, and it's not the real case over the ocean. So actually, we need to think more about the setup, a more realistic case in the future. And of course, the data should come from the tests in the field that is can give us more realistic simulation. Yeah.
May I ask a question?
Please.
Yeah.
It's unclear what kind of waves we are talking about. Are they near the shoreline? In this case, the depth of the sea in this area is critical. So also, if you observe the real destruction of the wave, it's more like cavitation effect. It's a mixture of water and bubbles. It's not just pure water, no, liquid or gas. It's a mixture with very unpredictable behavior. So, and also, you talk about temperature, but in reality, temperature is just a measure of kinetic energy. But we should talk about fluxes mostly. Temperature can vary only as a result of changing in fluxes. This is the only mechanism. Mechanism of changing the temperature. What is this?
So I think flux, right?
Scalar field. So
the flux is the dominant mechanism, I think.
Yes.
Yeah.
Yes. If this is ocean waves or other type of, I don't know, tsunami.
So actually,
so it's a different story.
Yeah. So let me discuss this with you first. So about what type of wave it is, right?
Yes.
So actually, for in terms of simulation, you know that we need to set up some wave that can break to start the simulation. So basically, if we look at the wave geometry, something like this. So actually, what we use is a deep water condition to initialize the simulation. Yeah. So
because previous
it's
slide,
not a coastal condition.
Yeah, you have very close to the surface. You have the how it's called no, floor, solid floor, on one of the slides.
Yeah. So you mean?
Yeah, no, look, no, not on this slide. Come on. Next. Yep, previous.
This one?
No, previous.
This one?
No.
Yeah, that one.
No, previous.
Previous?
Yes, this one. You see?
This one?
Solid body and the way.
No body. No, this is just a sketch figure that shows if we can also do something with solid bodies, but for this simulation, we don't have solid bodies.
Extract from your presentation. It's misleading.
Yeah, that's a little bit misleading.
Okay.
For our simulation, because
you.
There's a flat bottom without any.
I understand. Deep water. It's
deep water condition.
I understand. Thank you.
So a couple questions in the chat here, some related. So wondering if your level set method can track only the one air-water interface or multiple interfaces. I think leading toward the question about whether droplets can be captured and whether droplet breaking or droplets will affect your results.
All right. So for this question, right? So droplet. Well, actually, we can check multiple interfaces. So if you look at this movie, right? there are many interfaces, and you can see lots of bubbles here and lots of droplets after the wave breaking takes place. So will droplets after wave breaking affect any of your result? Actually, numerically, yes, right? So because we resolve those droplets, so numerically, of course, yes, but physically, the droplets are relatively small. So how much heat is carried by these small droplets, I don't think that's that important. So from our simulation, you can see that actually the whole process is still mainly determined by this kind of larger scale processes, like wave overturning and the plunging of the overturning jet, right? So and then there's a disturbance on the turbulent motions. So that is all these processes are relatively with a relatively larger scale than the droplets. Yeah.
So there's
Yeah.
another question in the chat too that is related, and I think you answered part of it. I'm asking about second order effects you expect on from spray mediated flux, but there is a question related part of this question as to how does the bubble or spray or droplet generation vary with wave age?
Okay, so this is a very interesting question. Actually, we try to work on this, but the challenging is actually you can see that for this simulation, we only have one wave. This is an example that we don't have a temperature gradient in the air. Oh yeah, we have temperature gradient, but we don't have wind. We don't have wind in this case. This is an example, just shows our simulation method. Basically, if we use a high resolution, we can solve those bubbles. But for the present simulation, if you look at the setup, actually the grid resolution is not that high. We cannot solve those very small bubbles. So I cannot go to the details of the effect of wind on the bubbles or on the sprays. So in the future, we probably will go to, if we can run a simulation with a higher resolution, we can take more, we can see more details of this. Yeah.
Great, thank you. Was there another question that someone was asking? Well, we're very close to the top of the hour when we need to finish up, but I think we do have time for maybe one last question. If anybody would like to ask something. Here we go. So a question is, what is the height range based on the simulation of the waves with increased velocity due to wave breaking? And can you compute for the potential conversion, so measuring the velocity from water wave to wind wave?
Compute for the potential conversion, measure velocity from water wave to wind wave. So okay, so I'm not quite sure about this question about what water wave and wind wave, but for the question about the height range of the effect of wave on the velocity, we can look at this page. So this vertical axis is non-dimensionalized with wavelengths. So you can see that for this like 0.4, below 0.4 wavelengths, that is the effect of wave breaking is significant. And above this height, there is almost no change in the wind profile after wave breaking. Yeah. So for the second question, I'm not quite sure about what do you mean by water wave and wind wave. Are you saying that the method, the way that wave is generated or something?
Yeah, sorry for that one. I think I should have omitted the second question. I was just thinking that considering that for the waves, when I saw the image there, that there's increased velocity for on the
Okay,
one of
for
the
this
images.
page, right?
That one, yeah, the high speed regions.
Yeah.
I was just thinking that, I guess considering that I'm focused on the field on wind, and for example, wind turbines. Do you think that these high-speed regions can be eventually be used, perhaps, for
Yeah.
wind, increased wind, if ever you're gonna place wind turbines there?
Okay, place the turbines here.
Sorry. Yeah.
So I'm not quite sure about this because wave breaking, so one thing that is very special for breaking wave is it's really challenge to predict it because you don't know where the wave breaking should occur or when the wave breaking takes place. So I'm not sure if we can really use the energy of wave breaking to drive the turbine.
Okay, sorry for that.
Great.
Okay.
Well, it is 6 o'clock Pacific time now, so I think we're going to have to end this. So thanks to everyone for coming. Thanks, Zixuan, for the
Thank you.
presentation.
Yeah,
I
thanks.
hope everyone enjoyed it.
Sure. Thanks.
Thank you very much.
Oh, Professor He.
Thank you. Thank you, students. Thank you, Professor Onet.
Thank
My
you,
pleasure.
Professor He. Oh, so you are at means?
Yeah. The professor's
Okay,
computer
I see.
have some issue. Yeah.
Yeah.
I see.
Okay. Thank you all.
Okay,
Thank you,
yeah,
everybody.
thank you, Professor Ole.
Thank
Thanks,
you.
Brad.
All right. All
Yeah.
right. Take care. Bye-bye.
Bye-bye.